Okay, continuing our derivation of how we're going to set up an integral to find flux, which we know in the context of fluid flow, we want to be mass per unit of time that's flowing through a surface. What we've determined is that if I chop my surface up into little pieces, and for each piece I choose a representative point, and I look at the vector field F at that point, I'm going to treat it as if the vector field is constant at that value over this entire little patch of surface. Okay, so here I'm looking at the surface dead on. It's sort of sticking out from the board. Here's a picture, and to match this, I had sort of chosen my Pij to be somewhere in the middle, and I'd chosen a representative force at that point, and I'm treating it as if the force is constant over that entire little patch of surface area. Okay. What we just determined is that I can write that force as this component, which is parallel to the unit normal vector, plus this component, which would be tangent to the surface. And if it's tangent to the surface, it's really not contributing to what's flowing through the surface. So this is the component of F that's contributing to stuff actually flowing through the surface. But I remember that the projection of F onto N, now N, remember, is a unit vector. It's the principal unit normal vector. And when I project onto a unit vector, I get a multiple of that vector. Actually, if I project onto a vector that's not a unit vector, I get a multiple of that vector. But because it's a unit vector, the formula for what I get here is fairly simple. It's just F dotted with N. If N wasn't a unit vector, this coefficient would be more complicated. I'd have a fraction, and on the bottom I'd have N dotted with itself. Since N is a unit vector and N dotted with itself is just the magnitude squared, that would just be 1 in this case. Okay. All right, so this is the signed magnitude of the projection of F onto N. This could be positive or negative. If it's positive, that says it's pointing in the same direction as N, so we're flowing in the positive direction. If it's negative, that says it's in the opposite direction of N, so we're flowing in the negative direction. And then it's the magnitude, because the magnitude of this is just 1. So that's going to determine how fast things are flowing and whether they're flowing in the positive or the negative direction. Okay. But if this is just the signed magnitude of this particular component of F, the units for it are going to be the same as the units for F. So I mentioned that earlier, but now we're taking a closer look at what that actually represents. The units are the same as the units for F, which were kilograms per meter squared per second. Okay. Now, what I'm going to be doing is I'm treating it as if I've got this many kilograms per square meter per second flowing through this surface over this entire little patch of surface area. But if that's kilograms per, so I'm sort of thinking of this as kilograms per meter squared per second, like so. That many kilograms per square meter every second. Okay. All right. Now, if that's happening over this entire region, if I were to multiply by the area, the surface area of this little patch, that would sort of tell me how much stuff is flowing through that patch. So I'm going to take F evaluated at Pij star dotted with N, understanding that N is not a constant vector. This is the N at Pij star as well. I'm going to multiply that by delta S, okay, by this surface area. That way, my units are kilograms per meter squared per second times meters squared. I'm going to get kilograms per second. That's how I'm going to approximate the mass per unit of time that is flowing through this little patch of surface area. Very cool. Okay. So then, of course, steps 3 and 4. Step 2 is always the interesting step. Step 3 is I'm going to add all of these guys up, and step 4, I'm going to take a limit. And I'm hoping that when I add things up, what I get looks like a Riemann sum, so that when I take the limit of my Riemann sum, I'm just getting an integral. So let's take a look. I'm going to be adding up the sum as I goes from 1 to m, sum as j goes from 1 to n, f evaluated at pij star, dotted with n. And that really is also evaluated at pij star. I might as well write that in, because the unit normal vector is varying. What's normal to this surface is a function of the point that I'm at, times delta s ij. Okay. Now I'm putting the ij here because generally when I chop up a potentially curved surface, I don't chop it up into nice regular pieces that all have the same surface area. If my chopping is induced by a chopping of the parameters in the parameter plane I would rig things so that each rectangle had the same area. But we generally don't ensure that each little patch of surface has the same surface area. And then we'd be taking the limit as m and n go to infinity. Okay. And so what that becomes is that is the limit of a double Riemann sum. This is going to be the double integral over s of f dotted with n ds. And that is what we said was the formula for our flux. Just a little bit of notation. Sometimes flux is denoted with a capital phi, capital as opposed to lowercase, okay, which looks like this, and this is called then flux. Okay, flux can be done with a variety of different vector fields. Here we've chosen to use the density function used to scale the velocity function, and that way it's measuring mass per unit of time that's flowing through my surface. If this was just the velocity field, it would be measuring volume per unit of time that's flowing through this. And we'll come back and take a look at what happens if this is an electric field in a later video. Okay. I want to just take a look, though, at how we would then evaluate this. Because I know anytime I'm doing a surface integral, I'm going to parameterize my surface and switch from a surface integral to just a plain old regular double integral in terms of my parameters. So let me just copy this down, and let's take a look at what happens if we describe our surface a couple of different ways. So we've said that flux, which we can write as capital phi, is the double integral over s of f dotted with n ds. Okay. Now, if S is the graph of R of uv over some region D. Okay. I can parameterize things, so I can rewrite this as the double integral over D. I would simply write f as f of R of u. So I'd use a function composition as normal. But now, I can describe my principal unit normal vector in terms of my parameterization. Okay. I'm going to write that this way. Plus or minus del r del u crossed with del r del v over the magnitude of del r del u crossed with del r del v. If you look in your book, you won't see the plus or minus. That's because the book supposes that we choose our parameterization so that it gives us the right orientation. But very often what happens is we're given a surface and an orientation. We're told we want it to be upward, or outward, or inward, or downward. So we know what orientation we want. And then we say, I got to parameterize the surface. Usually I just find a convenient parameterization. which means I have a 50-50 chance that I picked a parameterization whose principal unit normal vector points in the direction that I want for the orientation of my surface. If I picked one that points in the wrong direction, I would simply adjust with that minus sign. Okay, so you can certainly rig it so that you always pick a parameterization whose principal unit normal vector points in the right direction. I think it's easier not to worry about that and just pick a parameterization and then check. If it's the right parameterization, you use that. If it's the wrong parameterization, you use the opposite of that. Okay, but that's how I would describe f and n in terms of my parameters. Okay, but then in switching from ds to dA, I'm going to get a scaling factor. My scaling factor is going to be the magnitude of del r del u crossed with del r del v, and oh my goodness, that's going to cancel. So we're going to end up just getting the double integral over d of f of r of u dotted with plus or minus, and this isn't you flip a coin or you can use either one, this is you pick the one that's correct, the partial of r with respect to u crossed with the partial of r with respect to v, dA. Very nice. Kind of like with our work integrals when we were looking at f dotted with t, and t, if you'll recall, was r prime of t normalized, but the magnitude of r prime of t was the scaling factor that we get with line integrals, where when we switch from d little s to dt. And so that scaling factor also canceled out. So it's very, very, very nice that that happens. Okay. Now, the other common way that we'll have of describing surfaces is where one variable is a function of the other. Most commonly, z is a function of x and y, but it could be either x being a function of the other two or y being a function of the other two. So, I know that flux is the double integral over s of f dotted with n ds, and if s is the graph of, let's just say z equals f of xy over some region d, this becomes the double integral over d of f of, it would become xy f of xy, okay, because originally my vector field is a function of x, y, and z, and I'd just be expressing z in terms of x and y, dotted with plus or minus. Now what we determined was going to be our principal unit normal vector. We had a 1 here, if you recall, and a negative partial of f with respect to x, negative partial of f with respect to y, normalized, square root of partial of x squared, plus partial of f, partial of y squared, plus 1. But then again, my scaling factor is exactly this denominator, partial f, partial x squared, plus partial f, partial y squared, plus 1, dA, and that scaling factor cancels. So I just get the double integral over d of f of xy, f of xy, dotted with plus or minus negative partial of f with respect to x, negative partial of f with respect to y, 1, dA. And what's really nice about this is if I was told it was oriented upward, I want this. If I was told it was oriented downward, I want the opposite of this. So it's very quick to check which is the correct orientation if you are working with something where you've got z as a function of x and y. Excellent. So that is our derivation of how we will calculate flux integrals. We will actually do that in the next video.